Hello, my name is Michael Posman. This is my Lab 1 constant velocity report. This is the introduction. The purpose of the lab was to observe and analyze the motion of an object moving at constant velocity. To do this, we used the tracker software to extract the exact position time data from our real-world experiment. We also developed a computational model based on Newton's first and second law. And then we compare the experimental data with the model's prediction to verify the accuracy of it. Fundamental principles at play here are Newton's first law, Newton's second law, and the computational model that we made. First law is object in motion stays at motion until acted upon an outside force. Newton's second law is when the net force is zero, velocity remains constant. And the prediction of our final results is our experimental data closely matched with the model. So our process and initial conditions. Using the tracker of the video we took, which is right here. There's our video. Uh, we found that velocity using velocity equals change of position over change of time as the tracker, as we used the tracker data of each frame. Then we used a computational model to predict the experiment results, and we made a loop that updated the position and velocity at specific time intervals, so 0.1. And since the net force was zero, the velocity remained constant, and we got a final result of 0.66 meters per second after each iteration. Um, and then we also made graphs of our computational model and the data we got from the tracker in our real world experiment. Here's the code that we used, and our model's output was here. As you can see, velocity remains constant as position continues to grow, as position continues to get higher and higher. There are two graphs. So our model for the ball went that way is just perfectly straight line, and our experimental data was almost perfectly straight with an R value of 0.9989, which is very close to perfect linearity, and we'll explain why some of those could be wrong. And then for our main questions, what if the axes were flipped? The physics would remain the same if the axes were flipped, so the data would just be reversed one way or another. So, for example, in my video, the ball moved from right to left, but if we mirrored that video and the ball moved from left to right, we would just see the slope of our graph being positive, but it would be the same data. The system and surroundings. So the systems of the system in this experiment was the object itself and any of the forces acting directly upon the object, such as gravity and the normal force, which we'll talk about later, and the motion that it initially came in with the initial velocity. And our surroundings were air resistance and friction, which we kind of ignored, and the surface of the table that we were moving on. So what is this? When does it mean? What does it mean? In the experiment, the object is likely affected by the two main forces of gravity and the normal force, which cancel each other out in the vertical direction. So we really only look at the initial horizontal velocity, which remains constant through our entire experiment. So the key takeaways from this, even though there's multiple forces acting on the object, their vector sum is zero, and is why we can assume constant velocity or use constant velocity. This any slight deviation in our experiment come from friction and other outside forces. So the difference between the models and the experiment. So the model has both of them have a constant velocity or assumed constant velocity, zero net force, and 1D motion. It's just moving in a straight line across an axis. And the difference is real world forces like friction and air resistance might slightly slow down the object, which is why we didn't get perfect linearity, and the measurement errors in the tracker, which is to be expected, especially with a tracker that's kind of used for the first time. And yeah, the initial conditions were they could have been slightly different from in the could have been slightly different in the tracker and in our model. Thank you.